Hey everyone, and welcome. Today, we're going to decode the secret language of the universe. Well, chemistry at least. We're talking about reactions and equations. This is the stuff that explains how everything works, from a nail rusting to a cake baking in the oven. So let's get right into it.
So let me ask you something. You've seen ice melt, right? It turns into water, but you can just pop it back in the freezer and get ice again. No big deal. But have you ever tried to uncook an egg? Yeah, didn't think so. That fundamental difference, that's exactly what we're going to break down today. Okay, so here's our game plan. We'll start with the basics of change itself. Then we'll learn the language of chemistry. After that, we'll get into the different types of reactions, the ones that build things up and break them down, and the ones that do a little swapperoo. And finally, we'll see how all this stuff pops up in your everyday life. All right, let's kick things off with Section 1, the world of change. See, before we can even talk about a chemical reaction, we've got to get a handle on the two big types of transformations out there, physical and chemical. So here it is, the key difference. A physical change, like melting ice, doesn't actually change what the substance is. It's still H2O, just in a different form. But a chemical change? Whoa, that's a whole different story. You burn paper, and that paper is gone. Poof! It's turned into totally new things like ash and smoke, with completely different properties. You can't get that paper back. And that process, that transformation where you get new stuff, well, it has a name, a chemical reaction. It's pretty simple, really. You take your starting ingredients, we call those the reactants, and they get converted into totally new things, which we call the products. So, how can you tell if a chemical reaction is actually happening? Well, chemists are like detectives, and they look for clues. Things like a sudden color change, or maybe it gets really hot or cold all of a sudden. You might see bubbles of gas forming, or, and this one's cool, a solid just appears out of nowhere from two clear liquids. These are the dead giveaways. Okay, so now we know what a reaction is, but how do we, write it down? That brings us to Section 2, the language of chemistry. We're about to learn how to write and balance equations. Now, before we even think about writing an equation, there is one golden rule, the single most important law in all of chemistry, the law of conservation of mass. It basically says you can't create or destroy matter. What you start with, you have to end with. Every single atom that goes into a reaction has to come out. They're not gone, they've just found new partners. And that law is exactly why we have to balance equations. Think of it like a puzzle or balancing a scale. It's a simple four-step process. First, just list out all the elements you're working with. Second, count up the atoms for each element on the left side, the reactant side. Third, do the exact same count for the right side, the product side. Finally, you start adding numbers out in front of the molecules, we call them coefficients, until the counts on both sides match up perfectly.
Okay, let's try it with a real example. Iron reacting with water. Look at this equation. On the left, we've got one iron atom, but on the right, there are three. And for oxygen, we have one on the left and four on the right. See, this is totally unbalanced. It's breaking the law. The atoms just don't match.
But watch what happens when we add a few coefficients. Bam! Just like that, it's fixed. Now we've got 3 iron atoms on both sides, 8 hydrogen atoms on both sides, and 4 oxygen atoms on both sides. It's perfectly balanced. The law is satisfied and all is right in the chemical world. All right, Section 3. We know what reactions are, we know how to write them down. Now let's get into the different flavors. We're going to start with the Lego builders and the Lego breakers of chemistry, combination and decomposition reactions. It's super straightforward. A combination reaction is when 2 or more things come together to make one more complicated thing. Think A plus B gives you AB. And decomposition? Well, it's the exact opposite. You start with one complex thing, AB, and it breaks apart into its simpler pieces, A and B. And you see combination reactions all the time. A classic one from the lab is burning a magnesium ribbon. It combines with oxygen in the air and creates this dazzlingly bright white flame. Super cool. Or how about whitewashing? When you add water to quicklime, they combine and this reaction gives off so much heat that the container actually gets hot. Now, think about it. If building things up can release energy, it makes sense that breaking things apart requires energy, right? You got to put some energy in to snap those chemical bonds. And we actually name the reaction based on the kind of energy we use. If you use heat, we call it thermal decomposition. Use electricity, that's electrolytic. And if you use light, it's photolytic. And thermal decomposition can be super dramatic to watch. Check out this table. You take these green ferrous sulfate crystals, you heat them up, and they completely change into this reddish-brown solid. Or even cooler, you heat up colorless lead nitrate, and it breaks down into a yellow solid and these big plumes of brown gas. These color changes are a dead giveaway that something big is happening chemically.
So what about using electricity? Well, if you run an electric current through water, something really cool happens. It breaks down into two gases, hydrogen and oxygen. But here's the kicker. You always get exactly twice as much hydrogen as you do oxygen. That perfect 2-to-1 ratio isn't a coincidence. It's proof of water's formula, H2O. Two H's for every one O. Okay, on to our next major category in Section 4. These reactions are all about swapping and switching. I like to think of it like a big chemical dance party where everyone is changing partners. So there are two main dance moves here. In a displacement reaction, you have one really reactive element that just cuts in, bumps a less reactive element out of the way, and steals its partner. But in a double displacement reaction, it's even crazier. Two couples just completely switch partners with each other, a total swap. And you can actually see these chemical dances happen. For displacement, if you stick an iron nail into a blue copper sulfate solution, the iron kicks the copper out, and the whole solution changes from blue to green right before your eyes. For double displacement, you can mix two totally clear liquids, and instantly, bam, they swap partners and a white solid just appears out of nowhere. And that solid that seems to appear from thin air, that has a special name. It's called a precipitate. It's just an insoluble solid that forms when you mix two solutions. So in that last example, the white stuff was barium sulfate, and that was our precipitate. Okay, we're on the home stretch. Section 5, Chemistry and Daily Life. Let's tie all of this together by looking at a type of reaction you see every single day, probably without even thinking about it. We're talking about oxidation. Seriously, oxidation is everywhere. That rust you see on an old car, that's corrosion, which is just the slow oxidation of the iron. And you know that kind of nasty smell and taste of old potato chips or nuts that have been open too long? That's called rancidity, and it's happening because the fats and oils are oxidizing. They're reacting with oxygen in the air. Think about it. From the bubbles in your soda to the battery that's keeping your phone alive right now, your world is literally powered by countless chemical reactions. So the next time you see something as simple as a rusty gate, remember the incredible atomic dance that's making it happen. And that leaves me with one final question for you. What other hidden chemical reactions are powering your world right now?